Hey everyone! Welcome back to ZoomInData. And this is episode 29 of our KQL Concepts Deep Dive series. Today we are doing a deep dive into approximate aggregations, tdigest for percentiles, hyperlog for distinct counts, count-min-sketch for frequencies, and why they are production superpowers at massive scale. We are keeping everything pure concepts and interview focused. If you missed episode 28 on materialized views, it's worth catching up. Let's get started. Here is our roadmap for today. Approximate aggregations trade a tiny bit of accuracy for massive speed and memory savings, essential at planetary scale. tdigest computes approximate percentiles like P50, P95, P99 with bounded error. Hyperlog powers d-count for approximate distinct counts with about 1 to 2% error. Count-min-sketch enables approximate frequencies and top K heavy hitters with very low memory. We will cover when to choose approximate versus exact, real use cases, and trade-offs. KQL has built-in functions powered by these sketches. They are production-scale magic. Let's explore each one. tdigest is the go-to for approximate percentiles. It builds a compact sketch that captures rank information, perfect for P50 median, P95, P99 latency, or any quantile. Error is bounded and tunable, usually under 1% even at high percentiles. It's streaming friendly, updates incrementally as data arrives, no need for full sort or holding all values. Memory footprint is tiny, just a few kilobytes per group, so it scales effortlessly to billions of rows or high cardinality grouping. Use tdigest for monitoring dashboards. P99 request latency per service, 95th percentile error rates, session duration distributions. When exactness isn't legally required, approximate percentiles give you sub-second answers on massive data. Hyperlog is the classic for approximate distinct counts. It uses probabilistic observation of hash patterns, longest run of leading zeros in hashed values, to estimate how many unique items exist. Error is typically 1 to 2% with an extremely small fixed memory footprint, about 1 to 2 kilobytes per sketch, even for billions of uniques. It's streaming and mergeable, ideal for per-group distinct counts like unique users per region per day. This powers d-count, and approximately _count_distinct, in KQL. Use hyperlog when cardinality explodes, distinct IPs in logs, unique session IDs, high cardinality monitoring metrics. At scale, exact count, distinct, becomes impossible. Hyperlog keeps it fast and cheap with negligible error. Look at this side by side. It shows why hyperlog is a lifesaver for distinct counts at massive scale. On the left, billions of items stream in, get hashed, and feed into a tiny probabilistic sketch, just kilobytes. From those clever hash patterns, it spits out an estimate with only approximately 1% error. Fast, low memory, handles planetary scale uniques like unique users or IPs without breaking a sweat. On the right, exact count tries to keep a full hash set of every distinct item. See that huge memory balloon? It works perfectly, until it doesn't. At billions of uniques, memory explodes, queries fail, clusters crash, exact becomes impossible. The takeaway: when cardinality goes crazy, exact counting is precise but impractical. Hyperlog trades a tiny 1 to 2% error for orders of magnitude better speed and memory. That's why d-count exists. Use approximate when trends and scale matter more than the last digit, monitoring, dashboards, large telemetry. Precise when every count is legally or financially critical. Choose smart, and your queries stay fast without sacrificing meaningful truth. CountMin sketch approximates frequencies of items, how many times each key appears. It uses multiple independent hash counters. Each item hashes to several buckets, and we take the minimum count across them. Counts can overestimate, never underestimate, but error is bounded and decreases with more hash tables. Memory is tiny. A few KB can track frequencies for millions of distinct items. This powers Approximate top N frequent items, heavy hitters detection with low memory. Use CountMin for top errors per service, top requested URLs, most frequent event types in high-volume logs. When you need top 10 most common, without exactness, CountMin gives fast, memory-efficient answers on massive streams. So when do you choose approximate versus exact? Go approximate when cardinality is high, data is massive, and you're monitoring trends. P99 latency, unique uses per hour, top errors. Error of 1 to 2% is almost always acceptable for dashboards and alerting. Go exact when data is small, or when precision is mandatory, billing calculations, compliance reporting, financial totals. The trade-off is huge. Approximate delivers 100 times to 1,000 times faster queries with tiny memory. Exact often fails or takes forever. KQL makes it easy with approximately _percentile, D-count, top with approximate hints. Smart hybrid. Use approximate for live dashboards and exploration, then exact on filtered small subsets for final reporting. Choose based on scale and precision needs. Approximate is not wrong, it's smart engineering. Check out this balance scale. It captures the heart of when to go approximate versus exact in KQL. On the left pan, approximate, 1% error badge showing tiny inaccuracy is fine, massive data icon for billions of rows, lightning bolt for blazing speed, and low memory win. This side flies at planetary scale, P99 latency, unique users, top errors, all fast and cheap. On the right pan, exact, 100% perfect badge for zero error, small data icon because it only works on limited volume, slow turtle crawling, and tall high memory bar. Precise, but it crumbles when cardinality or volume explodes. The middle arrow says choose by scale and precision needs, and it's tipping hard toward approximate for most real-world monitoring and trends. Accept approximately 1% error and you get 100 times faster queries with tiny memory, perfect for dashboards, alerting, high-scale analytics. Reserve exact for billing, compliance, or small filtered sets where every digit counts. The philosophy is clear. At massive scale, perfect precision is often the enemy of usable speed. Approximate isn't sloppy, it's smart engineering. Pick the right side for your use case, and your telemetry stays fast, affordable, and insightful. Why does this topic matter in interviews? Approximate algorithms are core for big data and observability interviews. Common questions include, when do you use D-count versus count? Distinct. Explain T-digest error bounds. Why go approximate at scale? Understanding the sketches. Hyperlog log, T-digest, CountMin, shows advanced knowledge. It's critical for telemetry, monitoring, and large-scale analytics roles. Explaining trade-offs. Tiny error for orders of magnitude better performance and memory, demonstrates production thinking. If you can say, I use approximately _percentile for P99 dashboards on billions of latencies. Exact only for billing after filtering. You prove you build systems that scale without wasting resources. To wrap up, T-Digest gives bounded error percentiles, perfect for fast P95, P99 at scale. Hyperlog delivers approximately 1 to 2% error distinct counts with tiny memory, powers decount. Count-min sketch approximates frequencies and top K heavy hitters with very low memory. Approximate aggregations are smart for monitoring, trends, and dashboards. Exact remains mandatory for billing and compliance. The trade-off is clear. Tiny error buys you massive speed and memory savings, often 100 times or more. These sketches are quiet heroes that let KQL handle planetary scale telemetry without exploding cost or latency. Master them, and you unlock true big data analytics. That's episode 29 done. Thanks for spending time with me on ZoomInData. Next in episode 30, Time Series Analysis Patterns, we will explore make series, fill forward, interpolation, anomaly detection, and forecasting basics. Homework to lock this in. Explain to someone or out loud. Why use approximately _percentile instead of percentile? Think of a monitoring metric, e.g., P99 latency, where approximate is perfectly acceptable. Answer this one. What is the main benefit of hyperlog over exact distinct count? If this helped, like the video, share it with anyone prepping for Azure interviews, subscribe for episode 30, and drop a comment with your biggest takeaway today. Thank you so much for watching ZoomInData. See you next time. Keep zooming in on those concepts. Bye for now.